Equilibria involving weak acids and weak bases. Specifically, we're going to talk about solubility products. So, when we have an acid or a base, typically it's dissolved in water. So, we have the hydronium ion if it's an acidic substance, and we have the hydroxide ion if it's a basic substance. So we're going to talk about how to do the equilibrium expression for both of those. It is a little different than your traditional solubility products. So here we go. Why is it different? Because if it's a weak acid or a weak base, it's not going to dissociate completely. Strong acids, strong bases do dissociate completely. Salts dissociate completely. Therefore, when we are calculating concentrations, the ion is equal to the concentration of the solution. However, for weak acids and bases, that's not true because there's not 100% dissociation. As a matter of fact, it can get as small as to like 5% dissociation. So, a very common weak acid that we tend to talk about is acetic acid. So that's what you see here. We have acetic acid being dissolved in water, giving us the hydronium ion and the acetate ion. So how we write the equilibrium expression is we write our products over our reactants. We don't put water in there. Water is a liquid. This is only for our aqueous substances. So that's the ions and the acid. We're not going to include water. And then just like every other solubility, every other equilibrium constant, it is a constant. So it's something that you can look up. You'll either be given the constant and asked to find concentrations, or you'll be given concentrations and asked to find the constant. Either way, the constant for a weak acid or a weak base is always going to be extremely small. And that's because the amount of ions, which are the numerator of that equation, those are really small. So the same thing happens with bases. I should mention that if you have something that is not a one-to-one ratio, so for example, with acetic acid, hydronium, the hydrogen ion has a +1 charge and the acetate ion has a -1 charge, so it's a one-to-one ratio. But if you have something like phosphoric acid, H3PO4, that's a weak acid, but it doesn't dissociate like all three hydroniums at one time. We tend to dissociate it in steps. So each dissociation of each hydrogen will have like a different constant. So you're not really going to have like the squares that you see when we do, or the cubes or anything like that we see when we do solubility products, because we're usually just doing like one hydrogen at a time. So the expression will always look like this, where you have the hydronium ion, whatever the other ion is. In this case, it's the acetate ion on your numerator, because those are your products, and then the original acid in your denominator. And again, solving those concentrations. So here we see it again in a general format, where you have HA being like the hydrogen ion plus any negative ion, giving you an acid, dissociating into the hydronium ion plus any other negative ion. And you see the general formula here in blue. Again, it tends to lead to a very small equilibrium constant because it has a small concentration of the hydronium ion because it's weak. It's not dissociating completely. That tends to give us a pH of 2 to 7, a weaker acid. And then for a base, again, it's the, there's an arrow missing there in the reaction. Sorry about that. But it's the products over the reactants again. It's the whatever the positive ion is for the base and the hydroxide ion being produced. So those go in the numerator and then the base goes in the denominator. Again, equaling a constant. Again, that constant is going to be small. So it's going to be a weak base. So 12 to 7 on the pH scale, not a strong base, which would be like 13, 14, something like that. So that's it. Those are the equilibrium expressions for the dissociation of a weak acid and a weak base.